Hello, everyone. Welcome to a new TVS colloquium. Today, we have the pleasure of having Bernardo Fraga. He's a researcher at CBPF in Brazil, and he will be telling us about transient classifiers in the Fink broker. So please, Bernardo, take it away.
Thank you very much, Priscilla, for the invitation. Glad to be here, and hopefully I will be a member of TVS soon. And this is about a paper that we recently published at the end of the last year. You can find the link here. This was done together with the Fink group here in CBPF, which is me, Clécio, and André, and obviously the rest of the Fink team, which it's scattered around the world, basically. And this is a quick outline of what I plan to talk. I will try to motivate what we're doing by considering the challenges that we have going from ZTF to LSST based. I will do some PR for the Fink broker, of course, but this will be quick, and then I'll jump right into the work itself, which was done using the elastic data set. If you know it, you notice that the acronym is actually called a challenge, but I will call it a set itself. Fires that we developed with the elastic data, with the goal of them used for LSST. I will do a quick rundown of Fink infrastructure and how it performed given the elastic data set, what we are today, and what to expect coming with LSST coming in a very, very short notice. So from ZTF to LSST, we already have ZTF now, which is at the Northern Hemisphere in the Palomar Observatory. It has a 1.2 meter mirror, and it streams through the ZADS, the ZTF Alert Distribution System, around 1 million alerts per night. This doesn't actually arrive to the brokers. The brokers receive about 200K, which I think goes about quality cuts, but it goes only to, well, it's deepish, about 20.5 magnitudes in the GR, and sometimes I filters with a huge square degrees of 47, huge FOV of 47 square degrees, which makes it very quick to hunt things in the sky, and it can cover its whole footprint in about I think 2 to 3 days. For LSST is different. It will be in the southern hemisphere in Cerro Pachón in Chile. The mirror is bigger, is 8.4 meter, the primary mirror, and LSST is expected to stream 10 million alerts per night and up to 24 magnitudes in 6 filters instead of only 3 or 2, basically. This is at least a 1 order of magnitude increase in the number of alerts that get per night. I say at least because although the ZADS team says that stream 1 million, this doesn't actually go to the brokers. It goes to 200K, 200,000, sorry. So a minimum of 1 order of magnitude, maybe more. And this poses a lot of challenges, some related to, for example, infrastructure, because we need by we I mean the community itself needs to receive these alerts, which come from an automated difference imaging pipeline, process these alerts in a few seconds, because the LSST will basically continuously, and if you miss, small problem with storage, today's storage is cheap, so it's about 20 to ZTF, which I think is 1 terabyte per minute. And the thing is that these alerts need to be easily accessible to do stuff, whatever the community or you want to do, and they can have to be filtered quickly. And this is where community brokers come in. They will be.
Sorry, Bernardo.
Kostya says that.
Yes.
Yes.
I thought it was
Do you have
only
problems
me.
hearing me?
Yes, I
Okay.
thought it was only me, but apparently your audio is breaking a little bit. So maybe either if you have a different Wi-Fi connection, or if you can maybe remove your video, so because your bars for Wi-Fi are red. Hello?
Go ahead.
No worries.
I don't know where I stopped, but so basically, the last thing I was trying to say is that uh, the community brokers are the step between the final user and the luge of data coming from LSST. I will talk about this more in a bit, and also the we have scientific challenges too, which involves follow-up planning. The cadence for LSST may not be ideal for very fast transients, so it's very important that we have follow-up with different facilities. But we also need to know what we're looking at, and this involves characterization of the sources to better understand their physics. And given that we will go to fainter magnitudes, fainter objects, the possibility of finding new sources is actually very large. It's actually very big. But this all comes down to the first thing that we need to do, which is source identification. And this is the problem that I'm trying to tackle here, which is basically building light curve classifiers to identify the sources for these 10 million alerts that we will receive per night. And given this amount of data, we have to turn to machine learning. There is basically nothing that we can do. These are the best tools for the job. And this is what I'll show here, some machine learning classifiers for light curves coming from LSST. Now, I want to go quickly about the job of a broker. I imagine everyone knows, but just to contextualize here, what a broker does is the LSST imagines whatever, it produces an alert and sends this stream of alerts to the brokers. And the job of the broker is, broadly speaking, to add value to these alerts and then make them available to the community as a whole that does not need to fudge with this 10 million alerts per night. And this added value can mean lots of things. It can mean cross-matching with different catalogs. It can mean filtering for specific features like a magnitude or position in the sky. And it can mean classification, which is one of the core tasks of a broker. Now, for LSST, there are, I think, 7 brokers selected. They are more or less evenly spaced in Europe, North and South America. But since this work was done specifically within one broker, I will talk about that broker, which is the Fink. Fink is a community broker based in France. It's completely open science. And in fact, I will jump a bit here, the bullet points, and say that in 2023, so 2 years ago, Fink won a prize for open science given by France's Ministry of Higher Education and Research. You can read it here at the bottom if you speak French. I don't know if I made any mistake in the translation. And Fink has been processing, like many of the other brokers, has been processing alerts from ZTF since 2019. And in this process, it has developed several things, not only a web interface, but also Slack bots, Telegram bots, API endpoints. There are several tools for you to get notified by the for the alerts that you think are interesting, and to access the data yourself, either by APIs or by a web interface or by a data transfer that will show in a while. One feature of Fink that I don't know if this, I know some brokers like Alerts and Antares, I don't think they share the same view, is that although it's based in France, so the computing facilities of Think are based in France, the science development and software development in general can be done or is done currently by different groups all over the world. So we have a Think team here in Brazil, which includes me. We have Fink team in Australia. We have, I think, part of it in Russia, and well, of course, most of several of the members are in France. And you can visit here the website to check out these new features that I will show you some of it actually right now. So the basic thing that you see for Fink is a web interface where you can search for things. And there's a search form where you can type whatever you want to search. It's very smart, so you can complete things for you better than an autocomplete, a simple autocomplete. So you can search for many things from date, position to classes. So here I show an example. I want the last 10 objects which are classified by the transient name server TNS as supernovae 1A. And this is an added value for Fink, which cross matches with TNS and gives you the TNS classification. So given that, I chose one just to show ZTF 25 something something. You can check the light curves. And you see that it's only G and R band, with the brokers don't have the I band. And you can have the image from, I think this is Simbad or CBS, I can never remember. Here on the left, you have the cutouts here on the right. This comes from ZTF itself. And then you have several other options that you can say, that you can see the coordinates, you can download it, you can check out the brokers for that. And also, if you look at this top bar here, you have the how the alerts for this object were classified by the classifiers in Fink. So basically, it is called a supernova candidate because it was by one of the classifiers in Fink was classified as supernova, but it maybe didn't match all classifiers. But if you are looking for a more programmatically access to GTF data, Fink has several API endpoints that you can use. I list, I don't think, I think this is up to date. So you have all of them here. So basically have anomaly detection, or you have multi-messenger. You can search for solar system objects, and then you can try for cone search by name. The website is very complete. The documentation is great. It's very easy to use. There are notebook tutorials for you. So this is very simple to use and very useful. And finally, just the last thing before the PR for Fink is over. When we were doing this work, the Fink engineering team developed this data transfer at scale uh, tool for Fink. So, which means that you basically can download all ZTF data if you so like, but also the simulated elastic data sets, the three versions of them, just by going to the Fink data transfer website. You can further filter this what you like. If you go for ZTF, for example, you can choose to have only the light curve, which is what most of us are interested, but you can have the full packet, which include the cutouts too. So this, please don't go all at once, otherwise the engineering team will kill me because I advertise this a lot. But it's a great tool for you to start if you want to start looking at ZTF or even the simulated elastic. Okay, so now the public relations for Fink it's over. Let's go to the work that we did within Fink itself. And the work was a light curve classifiers. But since LSST is not here, we turn to the next best thing, which is simulated data. And the one that we used is called Elastic V1 because if you look here, there are two more versions. But by the time we were doing the work, Elastic V1 was the Elastic, was the data set. It has more than 50 million simulated, or basically, depending on how you count, but basically more than 50 million light curves for several different objects. The main point of Elastic, you can see that it's a challenge. So okay, let me try to get back. Elastic is a challenge, right? It's the extended LSST astronomical time series classification challenge. But I will refer to the elastic data set as just elastic for short, so I don't need to keep saying data set. The, the elastic challenge itself had two main goals. One was to test the broker's infrastructure, see if they could receive an alert stream, process them with their classifiers, and send back the classification scores or classification results back to desk. And by doing this, they would definitely evaluate their machine learning algorithms. So this is kind of a side goal, but it was what we used Elastic for. Now, there are other works that use Elastic, the Elastic data set for testing, for evaluating the classifiers. But I want to clarify something here. There, for the Elastic dataset, there was a training sample provided in mid-2022. They were full light curves. It's a static dataset that the Elastic team provided for training purposes. After that, after sometime after this the availability of the training sample, the desk team started streaming through the ZADS for 4 months the alerts themselves. This would comprise 3 years of data, which including detections, force of photometry, and metadata, which are the redshifts and stuff like that. So for this work, what I'm using, and after some point they unblinded this test set, which are the alerts. So when I'm talking about the last data set, I'm talking about the alert streams and not the training sample that was provided as static full light curves, right? So for this work, the training sample are alerts, so partial view of light curves, not full light curves that we cut ourselves. So one thing to notice is, okay, so first of all, I forgot to say that the taxonomy for elastic is here on the right. We can see that individual objects, such as different supernovae types, the other like kilonovae and dwarf novae and different variable stars, they are grouped together in what I would call broad classes. These broad classes are the Western-like class, the long, the periodic, and non-periodic. This will be important because our classifiers will target these broad classes. And one thing to keep in mind is that an object can have multiple alerts as long as it is above the threshold of detection. An object, LSST will continue to emit alerts every night for that given object. So when we split for our machine learning algorithms in training and testing, we split by the object and not by the alerts. In this way, there's no leakage from a light curve that was partly in training and partly in testing. So all light curves for any given object are in either one of the sets. The training data set was given to the Fink teams around the world using that data transfer, but the test set remained like blinded for us, just so that all classifiers could be processed to the test set in the same environment, the computing facilities in France. Okay, this is just an example light curves for elastic. I chose more or less at random. You see, for example, these red these red dashed vertical lines is the time of the trigger. It's when it is considered detected. So you can see that, for example, variable stars such as the phase, they are detected very early and then they keep being detected forever because the periods are very constant, and AGN the same. And you have stuff, for example, like the kilonova here at the bottom, which is a very fast transient, usually, so you don't have many points, many detections. You have maybe 1 to 3 points, and they are very within like 1 to 3 days, which makes them very challenging objects to classify. Anything you see before these red dashed line is what we call forced photometry. And to keep going about elastic, these are some statistics. A very, very imbalanced sample because it tries to mimic reality, and reality is not very kind to machine learning. The sample is basically half of them are supernovae type 2 and 1A. So basically, the supernovae broad class is almost 60% of all objects, followed by the periodic stars. And the fast class is less than 1% of the total, which includes kilonovae, microlens, and this kind of stuff. To the right here, in the bottom right, you see two panels showing the AKO extinction and the host redshift. We don't have redshift for everything. It's only about 90% for both train and test. And this can be either the spectroscopic or the photometric. Here I did made no difference between them. It's capped at 3, but you see a peak at around 0.5 to 1, and actually a valley between 1.5 and 2.5. And to the left, the bottom left, you see the distribution of points per alert. You can see that the vast majority of alerts that we're dealing with, they have less than 20, 30 points. So we're doing classifications based on very short light course. This is summed up in all features, by the way, right? It's not per feature, it's the sum of all point detections in a feature. Detections in blue, and if you include false photometry, we have the thing in orange. So false photometry is important for the classification because it increases the number of points that the models see, and is actually better for classification. And the right panel just shows the number of detections per feature. You see that the U feature, as expected, you have a very small number, and then GNR are more evenly distributed. GNR more evenly distributed. Okay, so we have our data set. We split into training tests. So now let's build some models and think this work. In this work, several people developed different models, different classifiers. CATS, which is the CBPF Alert Transient Search, is a broad classifier by which I mean it is a multi-class classifier targeting those broad classes that I mentioned before. This is what I developed here in CBPF. But we also have Super and Nova, which is already it was not built specifically for the Elastic or for LSST. It was there before. It's already running in Fink since a very long time. It's developed by Orange Muller in Australia. We have a superluminous supernovae classifier. This was developed specifically for LSST, but then it was included in ZTF also. And again, another classifier that was imported from ZTF or adapted from ZTF rather, which is the earliest N1A. I will give a quick rundown of these three here, the ones that I did not develop, and then I'll spend a bit more time on CATS. So basically, Supernova is already published. You can check it out here. It's an open source model as a general purpose photometric light curve classifier. It has different options of the models that you can use. You can have Bayesian networks with Monte Carlo dropout or Bayesian by backprop, or you can have simple, let's say, long short-term neural networks, which was the model chosen for the elastic data. It is very general purpose in the sense that it takes the light curve, but you can also include metadata together with it. And so this is what was used. Use the host galaxy redshift and the neutral extinction to make the classification, and analyze trained binary classifiers targeting each of the broad classes separately, and a full-blown multi-class classifier for the 5 classes at once. Now we have the early supernova 1A, for which the goal, as I mentioned, adapted from ZTF, the goal for this is to catch supernova 1A before the peak, right, in the rising phase. That's why it's early. So it works basically as a binary classifier, so it's 1A versus the rest. It uses a random forest, but the features that it extracts from the light curve uses a tool called Rainbow, which is a multi-band fitting for a relatively simple light curve. It basically assumes that your objects can be reasonably approximated by a black body, and then you need to give a temperature and a volumetric flux evolution, and then it computes the band flux path for each flux that you want. Like in this case, for example, EGR is UI. And for the earliest in 1A, the temperature evolution, the temperature evolution is given by the bottom equation, and the volumetric flux, it's kind of a logistic function on top. And just to show how the fit works, if you look at the plot here on the right, the circles are the points used to do the fit, and you see the cross here is was not used to do the fit, so it's a test point, but it agrees very well with the fit that was done. So basically, it takes fit information from Rainbow plus metadata to do the rainbow forest classification. And one caveat about this is that if the light curve is past the peak, it does not care about it. It only cares about stuff that is rising. Uh, so that is rising. Okay. And finally, not the last one, it's the superluminous supernovae, which actually includes both superluminous supernovae and parent stability supernovae. It Since they're both more or less they're both very similar, uh, ATM decided to include them both as one classifier. It again uses rainbow to fit all the light curves, but in this case, it did not use a pre-computed function, but instead used something called a multi-view symbolic regression, which is a way to do symbolic regression using multiple data sets. And they applied this multi-view symbolic regression to a real ZTF superluminous supernova candidate called SNAD 160. And the best function that was found for the volumetric flux is given at the bottom. And also, this is, I think, the only one that uses active learning, in which you keep feeding the training sample with more. You start small and then you start adding objects to your training sample uh, iteratively until you are satisfied with the results. And last but not least is CATS. As I mentioned, CATS is a broad classifier that so it targets the 5 broad classes. It was based on something called a multivariate LSTM fully convolutional network. You can see the plot to the right, which I think is a lot more informative than following with the multivariate LSTM whatever. It takes both the light curves and the metadata, which is both extinction, the host galaxy photometric redshift, and the transient Z whenever available. This is not always the case. And we did some hyperparameter optimization in this. Whatever you see enclosed in this dashed rectangles was subject to optimization. So this includes the number of filters in the convolutional, the size of the kernel, the activation functions for the fully connected and the LSTM, and the number of these blocks themselves. And to the left, the numbers right to these rectangles are the best fit scenario. We did not use the whole data set for this because it would take forever. We would still be doing this right now. So we used 10% of the objects of the training set to find the best architecture. And then we retrained the model with this with the best hyperparameters using what is called a 5-foot cross-validation. It's a simple scheme of cross-validation by which you divide your training set into 5, or in case of K, for cross-validation to K groups, and you perform K iterations of training. At each of these iterations, you choose one of your groups to be the validation group, and everything else is used for training. This is good to test the robustness of your model, to show to check how sensitive it is if you change the validation data. And as I mentioned before, when we split into train and test, we split the objects, and here is the same. When you split in those five groups, you split in the objects, the unique IDs, right? And at each fold, we choose the model with the lowest validation loss as the best model. And then between these five models, whichever has the lowest validation loss is chosen as the best. And this was given to France for the evaluation. Okay, right. So let's go to the results. And what I'm presenting here is actually a confusion matrix, the two confusion matrices boiled into one. To explain this further, whichever you see in bold is one, right? So here, 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 and here. This is one confusion matrix, and whatever is in italics, here, 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 and here is another confusion matrix. The bold one is normalized to the predictions, and the italics one is normalized to the true values. So the main diagonal, folks, is this one here, sorry, the main diagonal, which is this, you get the precision or the purity in bold, and the recall or the completeness in italics. To the left, for example, you see the results for the superluminous supernovae classifier, which has a very good purity of around 90%, or around, no, actually, it's almost exactly 90%, but their completeness is below 50%. And this is fine given the amount of data we will have, rather. It's, we don't care that much in this case about being complete, at least for this classifier. If you, on the other hand, if you look at the early supernova 1A, you have 70% purity and completeness, which is more or less what was found on validation sample. And here you see the different binary supernova classifiers. For each of those five broad classes, you see that on the top left is for supernova-like, which performed very well. In the top right is the variable stars, which again was good. And the bottom right is the non-periodic or AGN, which although the completeness is very nice, almost 100%, but the purity is not that good. And then the troubling classes, or the classes in which had no trouble are the long and top middle and the fast in the bottom left. You can see that although the completeness for both of them is okay, the purity is not that good. And if you look at now for both the broad classifiers, both cats and supernova, you see the same trends, is that the fast and long classes are the ones that give more trouble. Uh, for example, for cats, although the purity for the fast class is good, is above 90%, the completeness is 70%, which is not that good. And the long class is even worse because it has an 83% purity and less than 50% completeness. What is happening here for cats is that a lot of the long alerts are being classified as supernova-like, which kind of sort of makes sense because the most popular class of the long broad class is the superluminous supernova. So in a real sense, it is a supernova, right? It's just not classified as one. And the same is for purity, right? Part of these long classes are being classified as supernova. Part of the class, the alerts classified as long are actually part of the supernova. So, okay. Going on, what we want to do, basically for LSST, for example, what is important is to see how early we can classify things. And so, in this sense, we checked how our classifiers performed if you change the number of detections or the redshift, for example. So if you look for supernova broad, you have already a very good precision with just one or two detections, which is great. Detections, right? Not points in the light field. Detection. And this obviously change as this behaves more or less as you would expect. It says you increase the number of the points in your light field or detections, your model gets better. If you look at the completeness, though, this is not true for the supernova-like, which what is happening here is that basically most of these are being classified as long because of the superluminous supernova. If you increase the number of detections, it means that your light curve is longer, so the model is confusing the long-lasting superluminous supernova or pan-stability supernovae with supernova, no, let's say standard supernova. And the same you see for the redshifts. This same confusion between the supernova light and the long class you see here, since you have for since luminous supernovae are more common and higher redshifts, you have a confusion here and increase the redshift. And you see for cats, for example, which is the one that I'm most interested in, you see that you have a very good precision or purity with about 5 to 10 detections for all classes except for the long class. And since the long class includes objects that are long lasted, this is expected, and the behavior is exactly what you expect. If you increase the number of detections, then obviously the results get better. And you see the same trend here that you saw at supernova for the redshifts, for the confusion for higher redshifts between the long and the supernova light. Finally, what I want to mention is we have well, not actually four, but have 9 different classifiers. Can we combine them somehow to improve our results? Well, yes. And one thing we can do is use the broad classifiers as a first step before passing, giving the results of the broad classifier to the binary classifier, more specified or specific broad classifiers. Binary classifiers. So one example for this is to use cats before the superluminous supernova one. So basically what we do is we take cats, we take everything that gets classified as long, and this is the sample that the superluminous supernova classifier will work with. And what we have is a small increase in purity of around 690. It was 90% and now it's 95, 96, but we managed to catch more of these objects too. Within the the sample that the supplement supernova worked with, we have almost 70% completeness. And one thing that is a, a, a possible, a potential, let's say, way to improve the results is to combine, for example, several binary classifiers into one multi-class classifier. This is what is done here with the supernova binaries. We basically take all those uh, those here and say that the highest probability of them is actually the result. So you can see that compared to the supernova rods, these results are better in general, both in purity and in completeness for basically all classes. Uh, okay, I'll mention this later on. And finally, since we have two binary classifiers, we can we have three multi-class classifiers. Sorry, we have cats, we have supernova broad, and now we have this one. So we can probably increase our results for the purity of our sample or the completeness, basically by just taking the alerts where these two agree. Uh, if they don't agree, we leave it out. But if they do agree, then we say that that class is the class of that alert. And the result of this is to increase both in purity and completeness for all classes and remove some of the confusion that we saw before. It's also an interesting fact is that cats and these supernova binaries they agree for about 95% of all alerts. What they disagree mostly is between the fast and the long class, which are the hardest classes to classify anyway. And now I just want to mention about infrastructure performance because uh, this is a key thing for LSST. We cannot just create a huge deep learning model and expect it to run to classify 10,000 letters in 30 seconds, which is more or less the rate that LSST will provide with stream the alerts. So think with its infrastructure, which is uh, finite, not Google, it doesn't have a GPU farm or thousands and thousands of GPU. We are limited by the computational capacity of Fink. And so we tested, well, we and the engineering team of Fink, they monitored the throughput of all classifiers, and we found out that in this, for the classifiers that I presented here, about 82% of the alerts were processed by all nine of them in less than 30 seconds or less, which means that this is what we need for LSST. And about 90% was a minute or less. This might seem not ideal, and yes, it's not ideal, but we have to keep in mind that we did not think about optimizing for the throughput. What we wanted is optimizing for the results, so that the feature extraction in the models could be as big as as we wanted, as the developer wanted. But even then, it's a good result that 82% of the alerts were processed in less than 30 seconds without any optimization at all. And as I mentioned, the data transfer at scale for Fink, the data transfer service, was more or less an answer uh, of the Fink engineering team to how will we distribute the training sample for everybody, because it was 17 million alerts is not a simple thing to store somewhere in like Google Drive, for example. But apart from this optimization here, 82, oops, sorry, 82%, right now, Fink is running, well, Fink is running, rather, I did a more stringent parameter space optimization for cats. It's now ready to run in Fink. It passed all engineering tests in the operational rehearsal 5, which was, I think, in the beginning of the year, about 2, 3 months ago. It this new version of cats is slightly less performance than what I have here, of course, because mainly because it doesn't use metadata, but the drop in performance is very slight. There's nothing to be concerned about, and it can process everything in less than 30 seconds, in fact, even less. So I invite you. This is the address for the data transfer service for Fink. If you want to get Elastic or even VTF data, please go there and check it. And I will finish up by saying that we are happy with the results we get. The data set's very heterogeneous and imbalanced. What we found is for this data set specifically, the broad classifiers, they were confused by the same classes. So this at least points to the similarity being true and not a bias from the classifier. We found out that we can combine models to use their results, but we need to take care of processing time. Supernova, for example, is lightweight enough that we could combine them all, the 5 classifiers into one. This is probably not the case for cats. And well, basically, I mentioned only there are four overall models, but in the end, we have 9 different classifiers that are suitable for whatever need for different use cases or user needs. And we found out that adapting CTF to LSST is not as trivial. The beginning we thought, no, we just add more filters and that's it. But the results, we found out that this is not as simple as it sounds, especially, for example, for the early supernova 1A, where defining something as rising is not as easy as CTF. Okay? And I want to say that Fink, with all this, is as ready as it can be for LSST. And please visit Fink if you want. I think you're always welcome. If you want to add something to Fink, this is pretty easy. And that's it. That's the address. Thank you very much, everyone, for the attention.
Thank you so much, Bernardo, for this very interesting work, for presenting this very interesting work, for sharing with us. So yeah, thank you so much. And yeah, this is very valuable. So if anyone has any questions, please contact Bernardo later. Thank you so much.